So what are the payoffs? See, capital A1 is the action space for the first player. Small a1 is the specific action out of that action set that the player 1 has chosen. Right? So it says the ith player's payoff depends upon all the actions chosen by all the n players and the type of the ith player. Right? So type of the ith player. So what do you need is players' action spaces, the type spaces of players, their beliefs, which are formed by using Bayes' rule, and the payoff functions. Okay, the payoff functions. Okay. Right. So collectively, all this together will be a game called G, which will be described by.
Sir,
Yeah.
I have a doubt going back. So type is basically whether he's a high cost or a low cost.
What?
Yeah. In our previous example, action is whether he decides to be a high cost or low cost.
No. No, he doesn't decide to be high cost or a low cost. He is born with a high cost or a low cost.
Okay.
That is given exogenous.
So what is
Action is how much to produce.
Okay. Given that you.
Given
what
that
is
you are of a
type?
certain time, how much to produce? Is that
And
action
these are
is
expectation of the player.
expectations of each player about the types of other players,
Yeah.
given that that person knows his or her own type.
Okay. Yeah.
Right? And collectively, once you put all these things together, what you have is so if you put all these things together, you have a Bayesian game, a static Bayesian game, right? Where you specify the action spaces, the time spaces, the probabilities, and the payoff functions. Right? Then you have a static n-person Bayesian game. Okay, static n-person Bayesian. Okay? Right. Okay. Is this clear? Any doubts about this? So what are the new things that have come in from the static usual game that we have, the normal form game with perfect information? What are the additional things that have come in? Type spaces and probabilities. Okay, type spaces and probabilities. Okay. So let me set up a model for you. Okay. What's the time? Which more time do we have? 10 minutes. So let me ask you a question. Suppose you and your friend, I have asked the two of you to set up to do a project. Right? The project is due in a week's time. Okay? If both of you work very hard and produce a good project, you will get very high marks. If both of you shirk, then you will virtually get very little marks. You will fail in the project. Right? Okay? Sure? Each of you have to maximize the marks obtained in the project. You are not sure about your friend's type. So your friend could be of two types. Hardworking or lazy. Right? Your friend also believes that you are hardworking or lazy. Set this up as a Bayesian game and specify all these things. Okay, so players' action spaces. What things that you can do? Work hard or not work hard. So work hard and not work hard at your action spaces. What are the type spaces of players?
Hardworking.
Lazy or hardworking? The type space. What are the beliefs? You know your own type. For example, you know that you are a hardworking. Then the beliefs, with which the probability with which you think that the other person is a hardworking person or a lazy person, conditional on your knowing your own type, is the beliefs of this. Right? Okay. What are the payoff functions? The payoff functions are, so this game will be, suppose you are a hardworking type. And suppose you decide to work hard and your friend does not work hard. Then there is a certain payoff that you get. Right? If both of you decide not to work hard, given your time, then there is a certain payoff that you get. Right? Collectively, all these things are called a static Bayesian game. Right? So what you really be doing involved is in a static Bayesian game. Right? And this game would become dynamic if I said that you two would be a pair, and then you would have to keep on doing, you'll be doing projects throughout the year. Right? Then you would want to sort of, then dynamics would come. Then you would want to sort of, initially, you would say, I would like to pick a reputation for being lazy, so that my friend who wants to pass will actually then want to put in an effort. Right? So you might want to develop a reputation for being lazy. So you might want to take action which will manipulate your players' beliefs. Right? Okay, so those kinds of things are really what are going to come into play when we sort of complicate these things. And the solution to this game, right? So if you actually, so if you actually solve this, right, by doing what we usually do, you find the reaction functions and then solve it, right? The Nash equilibrium for such a game is called a Bayesian Nash equilibrium. So what we essentially learn to do is to find the Nash equilibrium for those kinds of things. This is going to be different from the way we approached asymmetric information previously. In the previous case, we said what, there is a principal, there is an agent. The principal does not know the agent's types, whether he's hardworking or not hardworking, so he's going to shout loudly enough in the railways to sell his ballpoint pens. So the contract has to have a participation constraint and incentive compatibility constraint. You solve it like that, you get the properties of the optimal contract. Here we are going to solve it as a Nash equilibrium. So really, there are two different approaches to the same issue. One is the game theoretic way, the other is the calculus way. Solving it as constraint optimization, putting in the appropriate types of constraints. But you saw there were difficulties in solving it that way. For example, the objective functions were not concave in effort levels. So we had to do some jugglery to find out what the optimal effort levels and the optimal contracts would be, and so on and so forth. Right? So therefore, we will now go to the game theoretic way. Right? Basically what we'll be trying to do is, basically this is a static game. So solving, essential key will be solving Nash equilibrium for this, and we'll make them dynamic games. We are going to solve for backward induction solutions. Right? And those are called, those are called dynamic Bayesian equilibrium. Right? So thank you very much, folks. I'll see you on Wednesday to take this on.